In this lesson, you'll be introduced to the 4 different types of energy changes, and we're going to focus on particularly phase and chemical changes. There are 4 different types of energy changes: temperature changes, phase changes, chemical changes, and nuclear changes. These energy changes are arranged in order from the change that involves the least amount of energy, being a temperature change, to the most amount of energy, which is a nuclear change. A phase change is a change in the state of matter without any change in the chemical composition of the system. These changes can either be exothermic, where energy is released from the system to the surroundings as new, stronger attractions between particles form, or the phase change can be endothermic, where energy is absorbed from the surroundings by the system in order to overcome the attraction between the particles. There are 6 common phase changes. The first phase change is known as fusion. Fusion is another word for melting, but it will be referred to as fusion. The change in state for fusion is from a solid to a liquid. In order for a solid to be transferred to a liquid, energy is required, and therefore this is an endothermic process. An example of this would be an ice cube melting. The opposite of fusion would be solidification. Solidification is also known as freezing. The change in state for solidification is from a liquid to a solid, such as water freezing, and this would be considered an exothermic reaction, since heat must be released to slow down the particles so that they can compact enough to be a solid. Vaporization is the state change from a liquid to a gas. You may know this as evaporation. An example of this would be water boiling. In order for water to boil, heat must be put into the process, so this is an endothermic process. The opposite of vaporization is condensation. Condensation is when a gas goes to a liquid, such as dew forming on the grass. In order for this to happen, heat must be released so that the gas molecules can slow down to a liquid. Therefore, this is exothermic. The last 2 types of phase changes are both known as sublimation. Sublimation is when either a solid goes directly to a gas or when a gas goes directly to a solid. If a solid is going directly to a gas, then heat must be put into the system, and this is an endothermic process. An example of this is when solid carbon dioxide is immediately transferred to gaseous carbon dioxide. If the state change is from a gas to a solid, this is an exothermic process, as heat must be released. An example of this is when gaseous iodine completely converts to solid iodine. Please be aware of the 6 different types of phase changes, which ones are endothermic and exothermic, and the proper names for all. Phase changes always involve energy changes, but never involve a temperature change during the actual change in state. For instance, water boils at 100 degrees Celsius. At 100 degrees Celsius, all of the liquid particles will be converted to gas particles before you'll see a change in temperature to 101 degrees Celsius. That is, all the particles undergoing a phase change remain at that same temperature until all the particles have changed phase. Thus, there is no change in the average kinetic energy of the particles for a phase change. Instead, a change in potential energy is taking place due to the changes in the attractions between the particles. A chemical change is a change in the composition of the system as reactants are converted to new substances or products. You studied the different types of chemical changes in Science 1206. These include combustion reactions, double replacement, single replacement, formation or synthesis, and decomposition reactions. Energy changes involves changes in bonding. Thus, the type of energy involved is also potential energy. Changes in potential energy are due to changes in the covalent and ionic bonds between the atoms and ions, respectively. Chemical changes involve more energy than phase changes, as you saw at the beginning of this lesson. because the ionic or covalent bonds are much stronger than the intermolecular forces involved in phase changes. For all reactions, energy is absorbed in order for bonds to break, and they are released when new bonds form. These changes can either be exothermic, where we know energy is released, or endothermic, where energy is absorbed. In this part of the lesson, we are going to look at calculations of heat change involving a temperature change. The amount of heat, which is usually measured in joules, exchanged between a system and its surroundings depends on a number of factors. First, it would be the mass of the material. When all other variables are equal, an object with a higher mass can absorb or release more energy than an object of lower mass. A temperature difference is also a factor that affects the amount of heat exchanged. With all other variables being equal, an object with a higher temperature will lose more heat to its surroundings than an object of lower temperature. The last factor that has an effect on the amount of heat exchanged between a system and its surroundings is the nature of the material, meaning the type of material and the state of matter the material is in. The type or state of a substance affects its ability to absorb or release heat. This is indicated by either the heat capacity, which is a capital C, or the specific heat capacity, which is a lowercase c. Heat capacity is the quantity of heat required to change the temperature of an object by 1 degree Celsius. The specific heat capacity is the quantity of heat required to change the temperature of 1 gram of a substance by 1 degree Celsius. Notice that these two definitions are very similar. The difference between heat capacity and specific heat capacity is that specific heat capacity is specific to 1 gram of a substance. That's the only difference between these two definitions. Heat capacity, therefore, is usually associated with the units joules per degree Celsius or calories per degree Celsius. And the conversion between the two is that 1 calorie is equal to 4.184 joules. You'll notice this come up in the upcoming STSE. The specific heat capacity is usually given with the units joules per gram degree Celsius or calories per gram degree Celsius. When all other variables are equal, a substance with a higher specific heat capacity can absorb or release more energy than a substance with a lower heat capacity. It's very important to keep this in mind, as it will make some multiple choice questions quite simple. If you are given a question where you're given the heat capacity, because different substances have different heat capacities and specific heat capacities, and you must be told this, you can calculate heat, which we know is Q, by using Q is equal to C delta T. So remember that heat is represented by Q and usually given as joules. Heat capacity is a capital C, usually given as joules per degree Celsius. And delta, meaning a change in, delta T is equal to T final minus T initial. If you're given a specific amount of a substance as well as its specific heat capacity, you would calculate Q using Q is equal to mc delta T, where Q is still the heat in joules, m is the mass in grams, and C is the specific heat capacity in joules per gram degree Celsius. Delta T remains as T final minus T initial. We are now going to go through several examples to ensure that we can interpret which formula we need to use and to ensure that we can use the formula correctly. Example 1. A frying pan with a heat capacity of 1.20 kilojoules per degree Celsius is heated from 22 degrees to 198 degrees Celsius. Calculate the heat change. So it's asking me here to calculate Q, and I've been given the heat capacity. which is a capital C. Therefore, I need to use the formula Q is equal to C delta T. I was told that the heat capacity was 1.20 kilojoules per degree Celsius. It's in kilojoules, and I'm going to keep it in kilojoules because while Q is usually given in joules, kilojoules is perfectly okay. For my delta T, it's the final temperature minus the initial temperature. The final temperature was 198 degrees Celsius, and the initial temperature was 22. You can, at this time, plug this completely into your calculator, but I do have a disclaimer if you are going to do that. Make sure that you're still keeping track of your significant figures. I strongly encourage that you do the delta T subtraction first, just to see if there's going to be a change in significant figures, and then multiply to give the final answer. So I'm going to say that it's 1.20 kilojoules per degree Celsius times 176 degrees Celsius. So remember that when you're subtracting, it's the least number of decimal places. There's no decimal places in 198 or 22, and neither in my answer. When I multiply this out, the degrees Celsius is going to cancel to give me an answer in kilojoules. And to three significant figures, that would be 211 kilojoules. Example 2. The temperature of a solid changes from 26.413 degrees Celsius to 32.786 degrees Celsius when 176 joules is added to the system. What is the heat capacity of the solid? Since I've been asked for heat capacity, I know I have to use the formula Q equals C delta T. However, I'm looking for heat capacity, so I need to rearrange for C is equal to. When I rearrange, I get Q divided by delta T. I'm going to calculate delta T off to the side so I can ensure my significant figures. The final temperature here was 32.786 degrees Celsius minus the initial of 26.413 to give me an answer here of 6.373 degrees Celsius. And this is an example of where delta T causes a change in significant figures. Both of my temperatures quoted had 5 significant figures, but now I'm down to just 4 in 6.373. We were told the Q was 176 joules, and I just calculated delta T to be 6.373 degrees Celsius. This gives me an answer to 3 significant figures of 27.6 joules per degree Celsius, which is also the units we talked about for heat capacity. Example 3. Find the quantity of heat required to raise the temperature of 100 milliliters of water from 20 degrees to 80 degrees Celsius. Here we've been asked to find the quantity of heat. This is Q. We have 100 milliliters of water, so we've been given a specific amount of water. So here I have to use Q is equal to MC delta T. A couple of new things that arise in this question. First, we have 100 milliliters of water, and I was told that mass has to be in grams. However, recall from Chemistry 2202 that the density of water only is 1 gram per milliliter. Okay, and this only works for water. So for every gram of water you also have 1 milliliter. So if we have 100 milliliters, we must have 100 grams of water. Additionally, in this example, we were not told what the specific heat capacity of water is. And the reason why we weren't told what the specific heat capacity of water is because this is actually given to you on your data table. So you'll have to open up your data table to determine what the specific heat capacity of water is. Additionally, you're going to find that the specific heat capacity is quoted for when it's a solid, when it's a liquid, and when it's a gas. Notice that we have a change in temperature from 20 degrees to 80 degrees Celsius, and during this temperature change, water will exist as a liquid, so you're looking for the specific heat capacity of water as a liquid. Off to the side, I'll calculate the delta T. You don't need to do this in a test situation. You can just do it right into the question. My final temperature was 80 degrees Celsius. My initial was 20 degrees Celsius to give me 60.0 degrees Celsius as my temperature change. Therefore, I can now calculate the quantity of heat with 100 grams, the specific heat capacity of water being 4.184 joules per gram degree Celsius, and my change in temperature being 60 degrees. I have 100 grams with 4 significant figures, 4.184 with 4 significant figures, and 60 degrees with 3 significant figures, so my answer must have 3 significant figures. When I multiply these, the grams will cancel, the degrees Celsius will cancel to give me an answer for heat in joules, which is what I would expect. Plugging this in on the calculator, we get 2.51 times 10 to the 4 joules. Our last example says, calculate the specific heat capacity, so we're looking for little c, of an alloy if a 15.4 gram sample undergoes a heat change of 393 joules, that's my Q, when it is heated from 0 to 37.6 degrees Celsius. Since I'm looking for specific heat capacity, and since I was given a specific quantity, I have to use Q is equal to mc delta T. However, I'm looking for specific heat capacity, so I must rearrange, and it's Q over m delta T. Off to the side, I will calculate delta T. Very simple. 37.6 minus 0 to give me, again, 37.6 degrees Celsius. Therefore, Q is 393 joules, a mass of 15.4 grams, and a delta T of 37.6 degrees Celsius. All of these numbers have 3 significant figures, so my answer will have 3 significant figures as well. And this gives me 0.679 joules per gram degree Celsius, which is what I would expect for the units on specific heat capacity. At this time, you're strongly encouraged to attempt thermochemistry worksheet number 2, where you'll find similar questions on both Q equals C delta T and Q equals MC delta T. Good luck!